Okay, we are going to solve this problem 3.5 from Griffiths, third edition. So the first item of this problem is to find the Hermitian conjugates of x. Okay, so what is this Hermitian conjugate of this operator x? The Hermitian conjugate of I, the Hermitian conjugate of this derivative. Now, remember, what does Hermitian conjugate mean? So if I have a certain operator Q, I say that the Hermitian conjugate of this operator, you can also use the word adjoint, is such that when I have Q acting on G, and but I move it to the front, I move it to the bra, it becomes the new one that is acting here on F is the Hermitian conjugate. Okay, so this equation is what gives us the Hermitian conjugate or adjoint of the operator. Now, if, this is the parenthesis in this story, if we find that this Hermitian conjugate is equal to the original operator, this is a special case, not all operators will satisfy that. So if this is true, then we say that this operator is a particular operator, is a Hermitian operator. And Hermitian operators are very important because they are the ones that represent observables. They are the ones that represent things that we can measure in the lab. Examples, the operator momentum. This is a Hermitian operator as we showed in class. Okay, all right, so then let's start. We want to find first the Hermitian conjugate of this operator, x. How are we going to do that? We are going to start using this equation here. Okay, so just let me copy that. F, then we have operator x acting on G. What does this notation mean? Derivative of this function, f, the conjugate of the function, x operator acting on this function G. Operator acting on G will just give us the variable x, G. Okay, now this variable x, everything in this integral is just in terms of x. I can move it freely. I can bring it to the front. It doesn't matter where I put. Now, how about putting this x inside this conjugate? Also, I can do that freely. Now, this variable is a real variable, so it doesn't hurt. I can put it inside that conjugate like this. So what does this mean? Well, if I go back to that this notation here, I can rewrite this integral as x now acting on f, g. Okay? So if I look at what we had here, you see that the Hermitian conjugate of our operator is just itself. I'm going to put a hat here. So it's just itself. So conclusion, the Hermitian conjugate of the operator x is just itself. This is not at all surprising. That's what we expect. Now the operator position is a Hermitian operator because it's associated with position, something that we can measure in the lab. Okay, so now let's go to the next case, which is to find the Hermitian conjugate of I. Okay, so same procedure, F, I next to G. This is an integral, F conjugate I and G. I is just a number, I can move it around with no problem. F and G. Now, how can I put this I inside the conjugate? Okay, well, then I have to be careful and change its sign. I put I, F, conjugate, G. Why? Because basically what we are doing there is I conjugate is equal to itself. Yeah, so I conjugate is minus I, which inside that conjugate gives us I. Yeah, so this I here, since I put it inside the conjugate, I put it minus I. Okay, what does that mean now? If I go back to this notation, I have minus I F G. So answering our original question, what is the Hermitian conjugate of I? Minus I. Yeah? So this one changed. Okay, let's go for the next one. The Hermitian conjugate of the derivative in x. Let's start again from the same procedure. Now the derivative is acting on g. If I write it in an integral form, we have the conjugate of function f, derivative of function g. To bring this derivative to the front of f, now we have to do something. We have to do integration by parts. So if we do integration by parts, we have f and g in some interval, and now we have minus the integral of derivative now in f is conjugate g. So this is just integration by parts. You know how to do that. Now, in which intervals we have? Well, let's put from minus infinity to infinity. So here we have from minus infinity to infinity, minus infinity to infinity. We are only interested in functions that belong to Hilbert space, meaning we are only interested in functions that are square integrable. These are the functions that when we go to infinity or minus infinity, the functions go to zero. So this term does not exist. Okay, so the only thing that survived was this integral here. Now, how can I put this derivative inside the conjugate? Well, this is not a problem. It's a derivative in f, so a derivative in x. So I can do that with no problem. What I have there is exactly the same thing as this. Okay? Don't forget we have this minus sign. So when I go back to this notation, what do we have? We have here minus the derivative in f g. Okay, so now you see that the Hermitian conjugate of this derivative is minus the original derivative. Okay, so now we are done with this part A. Let's go now for part B of this problem. Part B of this problem has also three parts. First one is, let's pick this operator, which is a product of two, okay? So, and we want to show that the Hermitian conjugate of this product is equal to the Hermitian conjugate of R multiplied by the Hermitian conjugate of Q. So you see that the order now changed. Now, so this is important. How do we show that? Well, let's start with our same procedure. We go F, Q, R on G. Okay? Now, what is this QR? I could give it a new name. I could call it a new operator S if I wanted. Okay. So if I see this whole thing as a single operator, what is the Hermitian conjugate? It comes to the front as this whole thing, like this. So you see what the idea behind this procedure is. I'm calling this whole QR as if it was a new operator S acting on G. And when I bring it to the front, the Hermitian conjugate of this operator is this S dagger F. Okay, so this is what I wrote there on top. Very good. But I could also go step by step. So let me erase this part. I could also go step by step. On this side, I could go step by step, meaning first, I'm going to bring Q. So what I have in mind is I keep R acting on G. Now R is the closest one to G. I keep R acting on G, and I'm going to bring Q to the front. Well, when I bring Q to the front, I have to have this Hermitian conjugate, okay? And R is there acting on G. But now I can bring R to the front. It is going to come in front of everything because now here I have a new bra. So here now I have R and then Q F, because Q was close to F, so it keeps acting on F. So I have R, Q, F, and G. So now I compare these two things. They're all equal, and you see that the Hermitian conjugate of this product changes the order. Is R, if I look at each one individually, is R, the Hermitian conjugate of R multiplied by the Hermitian conjugate of Q. All right? Okay, now how about the next one? The Q plus R. So now we want to show that the Hermitian conjugate of this sum, the Hermitian conjugate of this sum is the sum of each. Now is the Hermitian conjugate, the Hermitian conjugate is the sum of the Hermitian conjugate of each. Okay, now this is easy to show because it comes from, you can go straight to the definition of that, of this relation. Let me write it here. So, what is this? So what is this sum? This sum, I can write it as F Q R on G. So this integral. Well, but this I can open in two steps. Now I can open in two integrals. The integral of F and QG plus the integral of F R G. Integral of a sum is equal to the sum of the integrals. That's what we are showing. Okay. So how is this going to help us? So let me keep this and from this side, I'm going to bring this Q plus R, the Hermitian conjugate. I'm going to look at the Hermitian conjugate so that what I'm saying is I'm going to bring this Q plus R to the front here. Okay? So I just played with this left side. And here you see the Hermitian conjugate. Now, on the right, on this side here, what do we have? I have F, Q, and G. And I have F, R, and G. If I bring Q to the front, if I bring R to the front, what do we get? We have Q, conjugate, F, and G. And we have R, Hermitian conjugate, F, and G. So you see what we are talking before. Now this relationship came from here. It's just it's a consequence of what I just said. That the integral of a sum is equal to the sum of the integrals. So we open this integral of this sum as the sum of these integrals. Okay, now the next one. The next one is if we have now a complex number, C, and the operator Q, and we want to know what is the Hermitian conjugate of that. So we want to show that this is C conjugate and the Hermitian conjugate of Q. How do we show that? Well, let me focus on C first, okay? So if I have, if I write it like this, now same notation as before. What does this mean? We have the integral of f, we have c, q, and g. C is just a number, I put it wherever we want. I'm going to put it here. But this is an operator, I'll keep it on that side, acting on G. Okay, so this is a number C. If I want to put this number C inside the conjugate, I have to do the same thing that we did with I before. What is it going to be? I have to put C, the conjugate of this C, inside F, and the conjugate, because the conjugate of the conjugate will give us back C. So you see that I didn't change anything. And then I'm going to keep here Q and G. Okay, so all that just to say that if I move that C around, it becomes a conjugate. Okay? Okay, now what is the next step? The next step is to move Q around. How am I going to move Q around? This is going to be equal to, when I bring Q to the front, I'll have Q dagger. Okay, so then you see that the Hermitian conjugate of this CQ is that. The Hermitian conjugate of CQ, the Hermitian conjugate of CQ is the complex, the conjugate of this complex number and the Hermitian conjugate of Q. Okay, very good. The last item of this problem, item C, is the following. Go back to when we were talking about the harmonic oscillator and pick the raising operator and have a look at that, and then obtain the Hermitian conjugate of this. So construct the Hermitian conjugate of the raising operator. Let's go back to your book and have a look at what was this raising operator. This raising operator involved several constants, 2h bar, m, omega. Then it had I, it had the operator momentum, had other constants, m, omega, operator x. Okay, so this is the raising operator. And now what we want to do is we want to get the Hermitian conjugate of that. Well, numbers. Hermitian conjugate of numbers is remain being numbers. So all of these terms here, these terms are numbers. I don't need to worry too much about them. Now, what do we know about position and momentum? These are Hermitian operators. So the Hermitian conjugate of P is P. The Hermitian conjugate of X is X. These are Hermitian operators. They are observables. How about I? I is the one that we just did. I, the Hermitian conjugate of I is minus I. So this is the only thing that will change in this equation from all that we already showed before. So then, the Hermitian conjugate of this operator is everything, almost everything is the same. The only thing that changes is right here. This minus I becomes plus I. Everything else is just the same. Momentum and position. Yes? Now, if you go back to your notes, to your book, you will remember that this operator is the operator that we are calling A minus. So you see that this is the lowering operator. So you see that the Hermitian conjugate, and so this one is the raising operator. And we just showed that the Hermitian conjugate of the raising operator is the lowering operator. And this is what I mentioned to you. Very often, we don't use this notation A minus or A plus. Very often, we call this lowering operator just A. Né? And the raising operator, the Hermitian conjugate of A. This is good enough. Okay, but the notation in your book was to make it clear that one is bringing the energy down and the other one is bringing the energy up. Okay, but this is the end of this video.